Hello everyone. In today's session, we are going to have a very quick look into thermal run, and this is the synopsis of today's session. A very simple view of thermal runaway, the various domain wherever we can find thermal runaway, the major current relationships along with the circuit explanation, why the thermal runaway is referred as a chain reaction, and the definition for thermal runaway. Finally, the mitigation ways to avoid thermal runaway. In simple, the thermal runaway occurs wherever there is an increase in temperature. This increase in temperature leads to further increase in temperature, often leading to a destructive result. That is, due to certain increase in temperature, the process is enhanced, which results in further increase of temperature. This further increase in temperature becomes cumulative, and thereby it leads to destroy of the particular device we are utilizing. Simple, we can say some process which is being accelerated by increase of temperature, which releases energy in the form of heat. This heat further increases the temperature. That is, it is a kind of uncontrolled positive feedback. Now, let us have a look into the domains wherever we can find thermal runaway. The first and foremost domain is going to be chemistry or chemical engineering, where the thermal runaway is associated with some exothermic reactions which are being accelerated because of rise in the temperature. Next, civil engineering, the thermal runaway is due to the heat released by large amounts of curing concrete. In astrophysics, it leads to nova and several types of supernova explosions. Last but not least, in electrical engineering, the thermal runaway is associated with increased current flow. This increased current flow leads to increased power dissipation. Let us have the common emitter configuration as an example. The transistor currents are being related by this expression. IC is equal to beta times of IB plus 1 plus beta times of ICB naught, where IC, IB are referred as the collector current and base current respectively. Or else we can say IB as the input current, IC as the output current, where beta is the current gain for your common emitter configuration, that is equal to the output current, that is collector current, divided by the input base current. Okay, now we are having a new term called ICB naught. This ICB naught is nothing but current due to minority charge carrier. If we consider an NPN transistor, the minority charge carrier is going to be holes. If we consider a PNP transistor, the electrons are going to be the minority charge carrier. Minority charge carrier in the sense the concentration level will be very less. As a result, the current due to those charge carriers will be also very small. In most cases, it is negligible. Why it is being given the notation as ICB naught means, here we are discussing about common emitter configuration. This is the current flowing in your collector terminal when the input junction is being open circuited. And this is going to be the circuit diagram for an NPN transistor in common emitter configuration. It is being in emitter bias. That is, here we have connected an emitter resistor to ground. E and RC are going to be the base resistance and collector resistance respectively. The DC bias is going to be plus VCC, IB, IC and IE are referred as base current, collector current and emitter current respectively. VBE and VCE are referred as input junction voltage and output junction voltage respectively. Here what happens means, due to some variation in heat, the temperature gets increased, and one study says that for every 10-degree rise in temperature, the ICB naught is being doubled. That is, whenever the temperature increases, IC naught value will be double. Why? Because means, if the temperature increases, the concentration of the minority charge carrier will also be increased. There will be movement in the charge carrier. Because the movement of the charge carrier increases, the current because of the minority charge carrier also increases. That is, if the collector current increases, obviously the power dissipation, in particular the power dissipation also increases. If the power dissipation increases, it again increases the IC naught. That is, this process is being cumulative in nature. This cumulative nature thereby damages the transistor, which is referred as thermal runaway. Now let us see why the thermal runaway is called a chain reaction. The temperature increase because of due to certain reason. Because of the rise in temperature, what happens means, it increases the concentration of the minority charge carrier. Because of increase in minority charge carriers, the IC naught, that is the current due to minority charge carrier, is increased. When IC naught is increased, it obviously results in collector current as per the current relationship we had discussed before. And if this IC is increased, it results in power dissipation at the collector junction. We know the power is dissipated in the form of heat. If this power dissipation is increased, obviously the heat will be produced. Because of the heat, again the temperature will be increased, and this cycle is repeated. And that's why the thermal runaway is referred as a chain reaction. Due to certain reason, there is an increase in temperature. Due to increase in temperature, the minority charge carrier concentration is increased, thereby resulting in current due to minority charge carrier increases. As a result, the IC increases. Because of increase in IC, the power is dissipated in the collector junction. We know the power is dissipated in the form of heat, thereby this heat again intenses the temperature. If this process becomes cumulative in one stage, what happens? It leads to destroy of the transistor. In simple, we can define thermal runaway as self-destruction of the unstabilized transistor. Self-destruction we can know. Because of increase in temperature and the cycle rotates, the device is being destroyed. Why it is referred as unstabilized? For a stabilized transistor, there should not be any variation even with respect to temperature. If the parameter is going to get vary with respect to temperature or any other reason, then that is referred as unstabilized. In simple, the stabilized transistor should have a fixed Q point. Q point is nothing but the coordinates of VCE and IC. Here, if the IC collector current itself is varying, then obviously the Q point will be located either at the bottom of the load line or at the top of the load line, not exactly at the middle of the load line. And that's why the thermal runaway plays a very significant role in the stabilization of the transistor. Next, the junction temperature may be due to the rise in the ambient temperature or because of self-heating. The self-heating is nothing but due to the power dissipated at the collector junction. We know the maximum average power depends upon the construction of the transistor, whose range is between a few milliwatts to 200 watt. Actually, the self-heating arises due to variation in the power dissipated at the collector junction. Okay, now the thermal runaway has happened. Because of the thermal runaway, the transistor seems to be unstable, but we want a stabilized transistor. Okay, what are the ways to avoid the thermal runaway? And this being referred as mitigation of thermal runaway. The thermal runaway can be controlled by negative feedback technique. That is, whenever we want to avoid this thermal runaway, we shall increase the output current IC. If the portion of the output is being fed as an input, if the output current is increased, obviously the input current will get decreases. If the magnitude of IB decreases according to the current relation, that is IC is equal to beta IB, if IB decreases, IC also decreases to the same extent where we can find an increase in IC. Thereby, the increase in IC is being compensated because of this negative feedback technique. The next way to avoid the thermal runaway is by making use of heat sink. That is, these are the few images of the heat sink we use in our day-to-day life. Heat sink is nothing but a passive heat exchanger. That is, it transfers the heat generated by an electronic or a mechanical device, which allows the regulation of the device temperature at. Normally, the heat sink is designed to maximize the surface area so that it can have a cooling medium surrounded by it. In general, air will be a perfect cooling medium. Generally, an heat sink is made of copper or aluminum, but we prefer to use a heat sink made of copper because of the properties such as it is very thermally efficient and durable heat exchanger. Moreover, copper has a high thermal conductivity which allows the heat to pass through it quickly. The aluminum heat sink is said to be a low cost, lightweight. Even then, we are preferring for copper heat sink because of the low thermal conductivity of heat sink used by aluminum rather than copper. And this is a very short look into thermal runaway. We had seen what is meant by thermal runaway and how to avoid the thermal runaway and what are the ways and what are the types of heat sinks available. Thank you.